Hello and welcome to my talk. If EDR is the answer, you asked the wrong question. Before we begin, a bit about myself. My name is Matthew Eidelberg. I'm a technical manager in Optiv Threat Management team. I am also an adversary simulation services lead under this team. That's our red and purple team offerings, as well as I've authored many open source tools and frameworks. A lot of the research I do is focused around EDRs, evasion, bypassing anti-malware controls. I've spoken at DEF CON's Red Team Village, DEF CON Adversary Village, DerbyCon, B-Sides Las Vegas, GurCon, and RSA. Before we go any further, a little outline of the agenda. We're going to kind of talk about avoidance and then the bypass techniques, focusing specifically around EDRs, and then how we can silently blend in, and then introduce a framework called ScareCrow that I released earlier this year. We'll kind of demo that and then wrap it up with some recommendations, as well as any questions or answers. So, I like to kind of describe defense as almost in a three-tiered system. The first being the anti-malware. This is the tier one. This is the front line. This is the one where it's the front line of defense, where most of the proactive controls. This is where any type of events that would terminate processes or isolate a host would exist. Also where a lot of the telemetry that is used throughout subsequent tiers is gathered. The products here, EDRs, AV, whitelisting controls, they're all great at preventative, but they also provide a secondary function, which is to gather information that is then used by the tier 2. The SOC, the SIM, any type of blue team sort of investigation where there's a human element that will triage the events and then perform an investigation depending on what information is there. However, in this phase, they're prone to some false positives, especially with some human error. Sometimes there are things that get mishandled, or even there's not a lot of data on something, so that way there's misrepresentation of the data. And that's really where the tier 3 threat hunters or incident response come into play. That's when a security team is overwhelmed, or they don't know what they're looking at, and that trigger is kind of pulled. From an adversarial point of view, this is kind of game over. We never want the tier 3 to be involved because they know our playbook, they know all the stuff that we perform, so therefore it's a lot harder once that's engaged to still remain evasive. So let's talk about EDRs, the next generation of protection. So how does it work? Well, let's take a look at how the telemetry. So we know that from a process perspective, when an EDR sees a new process, it loads their DLL into the process. That's how the information is passed between the agent that's installed and the process itself. And then the agent will make a bunch of those decisions based on whatever defined policies in place to kind of proactively defend, prevent an application, any of those types of controls. But the real deep intellectual knowledge or the advanced, correlation of data points happens in the dashboard based on all the information and all that stuff. But you can kind of see from here, this is how this data constantly flows one way and then back. Before we go any further down the rabbit hole of avoidance and EDRs, there's two terminologies I like to define. The first one is Win APIs. These are functions that an application can use to interact with the operating system. These are often stored in the kernel base or kernel 32. The Windows operating system provides these DLLs and these functions, so that way applications can remain thin, as well as ensure that there is stability and no issues when an application is interacting with the operating system. At a very technical level, these API calls or functions align all the registers with the proper values on the stack before they're actually executed. They get executed by the system call instruction. A system call is a low-level piece of assembly that actually performs the operation. So every Win API function has a system call to match. This actually takes the request of the software and translates it into something that the CPU can understand and actually performs the actual operation. So when we're talking about creating a file, that's actually done at the system call level. Everything from the name, the location, the permissions, that's all handled and set up on the stack by the Win API. And system calls are stored in NTDLL. And those three locations are very important, and we'll touch base on that in a little bit. But as you can kind of see with this example diagram, you can see that app.exe calls virtual allocate. Virtual allocate is stored in kernel base. So kernel base performs its instructions, sets up all the registers, and then passes the execution on to the system call ntallocate virtual memory, which is stored in NTDLL. Once it actually performs this operation, it moves into the kernel space where the actual instruction is then executed. Now, based on the results, if it's true or false, or like a Boolean almost, if it's successful or not, it will send NTDLL the response. And that is then sent to kernel base to restore the registers, or if there was a failure, interrupt the process so that way no other instructions can happen. And if it is successful, it then moves on to the next instruction. So now that we understand how the normal operation works, let's take a look at how it would look when an EDR is in place. So once again, app.exe calls virtual allocate, which is stored in kernel base. However, we see that there's a redirection. This redirection is a jump instruction, and that forces the code flow to jump into the EDR, and that's where we're going to perform a bunch of steps, such as viewing what was loaded onto the registry, what's going to certain things, what is it being asked to do. If everything's okay based on the machine logic or whatever special sauce the EDR has at its disposal, it's going to return the execution back to kernel base to continue on. And we'll see that it also does that as well with NTDLL. So that way at any point in the chain, it's ensuring an integrity to make sure that nothing's being replaced due to modern techniques of adversarial changing things around. So that's really how an EDR works at a very simplified level of redirecting the code via hooks or jumps. Now, there are two areas where they can be hooked: user space or the kernel space. So there's pros and cons to both. The first one is the user. So the user, the pros of that is there is a lot less chance of crashing a product or an application or even the operating system itself. It's also easier to integrate with a lot of other products, SIMs or other data logging or aggregation. We've seen this a lot with the advancement of XDR and MDR. Having the ability to interact with a large ecosystem is really great for technologies that are trying to prevent any type of cyber threats. Now, the pros of kernel space is that it's a lot more resistant to attackers. It's a lot harder to load something into the kernel space these days due to Microsoft's added security features. Them being there has to be a valid driver, and that driver has to be signed by Microsoft, which means it has to be submitted and reviewed by Microsoft. It also gives them a different perspective, since the kernel is the central nervous of the whole operating system. Being at that point gives a unique memory visibility into the memory. But there are cons. So with kernel space, there's a way higher likelihood of causing instability when you're introducing drivers or hooking things at that level that can cause blue screens, disruption to services. There's also a lot less telemetry. So in the user space with Windows API functions, there is numerous different ones that can be hooked to give you a wide breadth of visibility. But in the kernel, it's a little limited. Now, the downside of the user space is that because it's a user space, everything has the same privileges as everything else, which means that the hooks and the malicious code have the same privileges. So if the hooks have the same privileges, it means that the malicious code could overwrite or tamper with those, thus making them easily to subvert. And that's honestly the major core component of a lot of bypasses that we are seeing right now and still prevalent for the past few years with regards to EDRs. So let's kind of take a deeper look on how we can actually exploit this. So first step, know the EDR. That is to say, what is being loaded. So if we see in this example, we have Google Chrome. We can look, there's many different ways to understand from our neutral perspective what's being loaded in. We can look at the name of the DLLs and see which ones stand out. It might be a vendor's name. We can also see based on the description if it's an EDR or some kind of defensive mechanism, or if it's signed or if it's installed into a certain pathway that you might say, C, program files, EDR company name. This all gives us an idea of that this DLL is an EDR's based DLL, and that's important for the next step, which is at that low level, understanding what it's hooking. So at an assembly level, a jump instruction or JMP instruction is E9 in hex. So if we know the name of the DLL and we know the jump, all we have to do is look for jump instructions that go to this EDR DLL. And once we have that, we can start to see what they're hooking and what they're not. So as you can kind of see from this example, there's two major ones. We can see that jump instruction we talked about, and there's an address that's not usually standard. And then we can see at the bottom half the normal ones. You can see where it's move RC10, comma RCX. That's the universal standard for an NTDLL based starting point for a system call. Then they'll follow up with an actual address, so it's incremental. So it'd be like A1, AB, or 1B, and that's the actual identifier code. So with all of this, we can understand how EDRs operate, what they're hooking, what telemetry they're gathering, and with all three of them, that gives us an idea of what it's not seeing, what it is seeing, that can then be used as an attack plan or a plan of attack to understand the weaknesses, to gain a foothold, and even do post-decks. So that's where we kind of jump into the bypass techniques. So now that we understand how they work, let's see how we can bypass them. Well, the first one I like to call is bring your own system calls. This is actually writing your own assembly system calls and functions into your program, whether it be your payload, your implant, whatever. But essentially, this code of assembly will contain everything that would do to set up the registers like the Windows API, and then actually execute it like that system call, moving it into the kernel space. Now, the value, move AEX 0x18 in this case, for NT allocate virtual memory, is actually specific to Windows 10. In Windows 8.1, it was actually 17 and so on. So that's something to always keep in your mind, is that it changes depending on the version. Also, there's some added steps depending on the programming language. As you can see right below, this is actually Golang. But by doing this, we are performing the same functions as the WinAPI and the system call. And because we are bringing in our code, the EDRs don't know it's there, so they don't know to look for it, so they don't hook it. And if we tell our code to use this, we're going right around those hooks completely. Second technique that we'll talk about is actually just dumping out the EDR out of the process. So we know that an EDR hooks a process when it's spawned. And we know which DLLs it hooks. So in theory, we can just reload them. It's not that simple. There's a couple of things we have to be aware of. The first thing is that when you load a DLL, you can't load it twice into a process. That causes a huge amount of instability because then the process doesn't know which one to use. You also can't unload system DLLs without actually causing the process to crash. So that kind of presents this thing of we can't unload it, we can't load two and then drop the other one. So how can we do this? We can use a Windows API called Virtual Protect. This allows us to change processes section of memory. We can do anything including change it from read-write to writable. But what's great is that we also know a clean version of these DLLs, which are sitting in C Windows System 32. So if we take those DLLs on disk and write them to those sections of memory that we now changed to writable, we can overwrite the hooks and still keep system DLL in there, basically overwriting the contaminated or hooked DLL. So if we look at this, we can even go this a bit more granular. Rather than reloading the entire DLL, we can just load a small subsection, the .text section of a DLL. This is actually where all the executable code lives. So all those system calls in NTDLL's case, they all reside in the .text section. So rather than the whole process, we're just doing a small section. That makes it a bit easier and harder to detect. So there's one thing we need to talk about before we go further is the offsets. Basically, what are they and how are we using them? Well, an offset is a value that is calculated based on where the start of the DLL is to how far inside the code it is. So depending on the address location from the top of the DLL. This means that when you are trying to do this type of technique we just discussed, when there are things such as ASLR or some kind of address randomization, where addresses are not absolute, we can use this reference point to know that, in this case, say, NT close is an offset of 96B40 from the top of NT-DLL. So all we need to know is where the DLL is, and then jump to that address, and we'll be right at NT close. And this is how it kind of would look. You can kind of see we have the file on disk. In the middle, we have the DLL running in memory, which is hooked. And if we take the file on disk and override that text section, all of a sudden we get a clean version. And here's how it would look. So we know, once again, NT allocate virtual memory is supposed to be 18 from the previous example. And we can see that there's that jump. So we know it's hooked, and we can see E9. So after this runs, we can see that it's been refreshed, and we can see the proper values of move RC10, and there's the 18 value. But EDRs have, they have the ability to protect themselves or have anti-tampering controls. So these would definitely trigger and prevent anything from going further. This is where, once again, we can now use that first technique we talked about, bring your own system call. If we bring our own version of anti-protect memory, which is the system call to virtual protect, we have our own system call that sets up all the registers and does all that stuff, and we can run that same technique again to flush them out, and this time it actually works. So another technique before we go on is utilizing ETW. So if you're unfamiliar, ETW is event tracing for Windows. It's a mechanism for diagnostics and troubleshooting, but it also allows for an enormous amount of events ranging from process to system-wide events that can be tracked down every second. How it works is that there are providers, controllers, and consumers. Providers are applications that can generate an alert or anything along those lines. So that might be PowerShell if you're more familiar with it, Excel, anything that would be used by a malicious user, or anything that would generate events or traffic. Consumers are applications that listen for this event. And a controller is an application that actually manages the sessions to trace these events, send them to the right consumer, so that way everything is properly logged and to ensure that the proper amount of data based on a policy is adhered to. So that's a lot of things to just say. A controller allows and manages the system based on whatever policy is in place to take the events from an application and set it to the right consumer with the right information. This has been really adapted by a lot of products as a secondary or, an XDR component of security controls, providing a different perspective rather than just user mode hooking. So that does pose a problem. So how does this work? Well, for those events to be generated, they actually rely on system calls that are located in NT-DLL. The difference here is that these products don't actually have to hook these APIs or system calls in order to get this information. Because they're part of the native system, that consumer and policy dictates whether or not these events are generated. So what can a malicious user do? Well, we can prevent this by simply patching the system call. And as you can see in this example, we're patching XOR RAX, which is basically an XORing the value of RAX to RAX, which creates a 0, and then returning it. Another technique is an old take on process injection. So for the longest time, process injection was really easy to detect. However, using those same techniques we talked about, unhooking and using custom system calls, we can actually use them to our advantage to perform a new technique or new take on process injection by first unhooking our process, then getting a handle to a process to retrieve a list of DLLs. Once we have that, we can then try to grab the base information, or address in this case, of 3. We all know which ones those are, so ntdll, kernel base, kernel 32. And then we can use the write process memory function to actually load those DLLs.txt sections back over, making sure that they're clean, with no hooks, and then we can inject shellcode again. This is because write process memory has a built-in debug feature. It's actually a race condition. That if a process is happening to be manipulating a page that is protected, write process memory will actually say, hold on, is everything set up correctly? Well, it is. So I'm going to let this go through. And the reason is that it was actually intended audience of this feature for debuggers, and as debuggers would freeze a target process before there was the high-end debuggers, this was a great way to actually edit pieces of memory. So how this works is that if everything is set up properly and you have the proper permissions, write process memory is smart enough to realize, well, I'm going to temporarily change the permissions to read write, update the memory section, and then restore the original permissions. So using that to our advantage, we can actually perform process injection by first removing the EDR out of the primary process and then remove the EDR out of the injected process, making both of them unhooked. Blending in. So it's great that we've bypassed EDRs, but you know what? It doesn't preclude any detection. SOCs, SIMs, or anything like that still gather enormous amounts of data. And as I always like to tell people, an EDR might think AW2R119IG.exe running from app data seems fine, but to a human, it's pretty suspicious. And if we actually look at this example, we can kind of see here, this DLL or CPL was loaded into a process. Now, didn't trigger any type of alerts, but from a post-mortem review, you can kind of see that it's pretty self-explanatory that something's standing out here, whether it be that it's unsigned, as well as there's no metadata on this file. So let's talk about code signing. Code signing brings less scrutiny and also kind of validates that it's a trusted file. The interesting thing is that EDRs don't have the capability to verify or do a proper code checking on each cert. Because of the computation, and it would slow down process. And no EDR would slow down an application to the point that would actually hamper business. So they're really focusing on that. Now, the flip side is that code signing certs are very expensive and not easy to get. As a result, what EDRs are doing is that they're actually looking for certain values that make sense. As a result, that they're only just checking parts things. Is it does the C name, the root chain, all these certain things look like what they should be, and creating almost like a whitelist of those predefined sets for trusted ones, say Microsoft, Cisco, Adobe, Google, your widely known ones. This is where we can actually take to our advantage, though, using a tool called Limelighter. This is actually a tool for signing binaries and DLLs. It actually generates fake certificates based on specifying a domain. So if you punched in this case, Microsoft.com, it actually will go and grab the attributes, pull them down, and create a code signing cert. Now, in this case, we know that this is going to not be Microsoft's legitimate code signing cert, but it has enough values in it that it would trick any type of anti-malware controls. It's also important to know that Limelighter has the ability to actually sign with real certificates. This also means that when you look at it traditionally, a lot of these types of code signing tools only existed on Windows, but now we can do it on Mac, Linux, anything like that, so it opens up a whole new possibility. Limelighter is public, and I'll provide a link at the end if you are curious to look at that project. Next, we'll kind of talk about file attributes. So as I mentioned before, it kind of looks suspicious that there was no data there. Oftentimes, leaving artifacts of the author who published it, whether it be some kind of hacker's computer name or anything else like that, or even blank itself can give away more alerts or indicators that something is suspicious going on here that actually leads to getting caught or further investigation. That's where sys files can come into play. These are files that actually dictate to an application certain things when it's being compiled. So it's something that can augment your application when you're compiling it. In this case, we can use them to actually augment the attributes of the final application that is compiled. Now, not every application has the ability to use them. To my knowledge, C#, Golang, and Java are the only ones that currently support these types of files with manipulation of attributes. So where can we get these attributes? Well, we can get them from any domain joined endpoint. Really simply, we can use the getItem.version info, and we can see it right here. All the stuff, it's all valid. And by taking all these values, we can load them into a large list to randomly jump through, whether it be Word.exe or PowerPoint. And once we have this, we can even do Office binaries, system-wide ones, anything that you would typically see. And it makes it really hard to distinguish. So, can you spot the real ones or the fake ones? Well, if you said all of them are fake, you'd be correct. So with all of this, from the techniques we talked about before, I'd like to introduce ScareCrow, a payload creation framework designed to bypass EDRs. I released this earlier this year. ScareCrow has the ability to create payloads and generate loaders to both side load into a process, which is a very important distinction from injections. This allows us to bypass application whitelisting controls by actually loading into legitimate ones. There are also different techniques, including process injection, as well as standard binaries, and we'll kind of talk about those different loaders in a little bit. But how it works is, once a process is spawned using ScareCrow, one of its loaders, it will unload the three DLLs, NTDLL, kernel base, and kernel 32. We'll use custom system calls to do this. Then what it will do is take the strings of shellcode and make them into an executable without even calling virtual allocate or write process memory. Use its own versions. Once it's decrypted all the shellcode and stuff, it will use alternate ways to execute shellcode that are typically not seen or well documented. Now, there are process injection techniques as well, but one of the major features of ScareCrow is that it can do side loading and unhook and process injection. Lastly, by default, what it will do is patch ETW to terminate the telemetry of that process. Removing all these different facets makes a red team or adversarial's techniques invisible to any security products. As you can see, ScareCrow has a lot of different loaders, from binary, which will just launch a standard binary. This binary will have all those attributes of whatever it's trying to masquerade as. So if it's Windows Excel, it will have all the attributes, the code signing, the version, all that stuff, even the location of where it's supposed to be on disk. It will all show up there. So it makes it hard for when it's on disk or even in memory to discern it from not the legitimate version. You also have a control panel applet, the ones you typically see in add and remove programs or even the administrator console. This essentially is a DLL that is executable with the CPL extension that when executed will spawn run DLL32 and load the DLL into memory executing it. And then there's a DLL, which is a standard DLL loader. And then the last three are kind of unique. So the Excel one creates an Excel plugin that when JScript is used will actually spawn an Excel process, load the plugin in, which will execute the DLL. Then an MSI feature that will actually create an MSI process to execute the DLL. And lastly, a WScript process to use a technique called register free com and a manifest file to sideload the DLL in without actually having to register it to the system to make sure it's a proper DLL. So there's a lot of great information and a lot more detail about these on the README for ScareCrow, which I'll provide a link for. So let's take a look at a demo. Here we'll demo a binary mode loader that's going to do process injection. We see its PowerPoint, and we see that it has the valid details that you'd see from PowerPoint, Microsoft, all that stuff, as well as signed by Microsoft. But when we execute it, what it will do is it will first move into the background, unhook itself, create the new process that we're going to get, and unhook it. So we see we got Notepad back, and it's completely unhooked. On our response, we can actually execute commands. Now if we take a look again, this is using that W script technique to sideload into a valid W script process. We can see that the W script process's private memory is expanding and growing and growing. And once it hits the proper value, once it's fully loaded in, we will receive our beacon and it will be fully unhooked. And once again, we can then execute commands without this time this EDR, CrowdStrike, from detecting or seeing any of our activity. So what can you do? Well, there's no easy fix, mainly because of the nature of userland hooking. Makes it really hard to fix. Vendors are slowly transitioning into alternate things with XDR, MDR, ETW, but as we can see with ETW even, there's still ways around it. But you as an organization, you have to remember that for these types of attacks to work, they have to have direct access to your endpoint, which means that there has to be other things that they have to jump through or bypass in order to get to the endpoint, whether it be phishing, multiple things. And that's really where the defense in depth strategy comes into play. Having a strong layer defense approach helps prevent the ability of exploiting this on your endpoints, thus reducing the impact overall. So I like to say strong perimeter controls and detection mechanisms will be your best tool against this. Before we close out with some questions, I just want to provide a link to both Limelighter and ScareCrow, as well as a link to my Twitter and my GitHub. If you have any questions, please feel free to reach out. Once again, thank you for your time,